Hi class. Today we will learn about the stellar evolution. Okay, the new chapter. In this chapter we will learn about the living main sequence, the evolution of a sun-like star, the death of a low mass star, the stars more massive than the sun, stellar evolution in star cluster, and also about the binary system. Okay, for the introduction, after reaching the main sequence, a newborn star changes little in outward appearance for more than 90% of its lifetime. However, at the end of that period, as the star begins to run out of fuel and die, its properties once again change greatly and embarks on a new evolutionary track. Okay, so observing the stellar lifetimes, okay, billions of stars in the universe have been observed, enough to see the example of every stage of stellar development, allowing us to set and refine our theoretical ideas. So the evolution is the change during the lifetime of an individual star. Okay, on the main sequence, a star slowly fuses hydrogen into the helium in its core, a nuclear fusion process called core hydrogen burning, or we can say it's a nuclear fusion process. Okay, so the burning is the nuclear fusion in a star's core. Okay, and also we have the hydrostatic equilibrium. It's a pressure's outward push exactly counteracts gravity's inward pull. So as the hydrogen in the core is consumed, it leaves the main sequence, okay, and both the star's internal structure and its outward appearance changes rapidly. So the post-main sequence stages of stellar evolution will depend critically on the star mass. Okay. Okay, so while the surface of the sun-like main sequence star occasionally erupts in flares and spots, so the average surface temperature remains constant, while the luminosity will increases very slowly with time. So after 10 billion years of steady co-hydrogen burning process, a sun-like star begins to run out of the fuel. Okay. Okay, so in continuation from the previous main sequence stages, and we have this stage 8, okay, the subgiant branch. Okay, is the star's helium content increases fastest at the center, where the temperature are the highest and the burning is fastest. So the original condition, okay, we have more containing of the hydrogen compared to helium. And then what happened after 5 billion years? So helium will be increased in the percentage of the element of helium. Okay, so this is happened at the core, okay, for this area. And then after 10 billion years, helium will be more and more, okay, content here, and at least it's getting more than the previous period of time, okay, as we can see, but still hydrogen is dominant. So when the hydrogen becomes depleted, okay, at the center, okay, as you can see here, okay, so the hydrogen in the yellow color here, okay, at the core. So hydrogen are being depleted, okay, or decreased in terms of the contents. So the inner core of a non-burning pure helium is formed. Okay, so the location of the principal burning move to the higher layers. So as the helium core is not hot enough to undergo fusion, the outward pushing gas pressure will be weak, and contracts and release the gravitational energy and driving up the center temperature and hitting the overlying burning layers. So this is known as the hydrogen shell burning stage. Okay, the hydrogen shell will generate the energy faster than the original main sequence star's hydrogen burning core. So this shell energy is a production continues to increase as the helium core continues to shrink and shining even brighter. So here you can see the star, okay, in the general feature, and then with this side, okay, the core in the middle. So here we can see the hydrogen burning shell located here, and the non-burning envelope, the outer layer and the inner layer is a non-burning helium. Okay, so this is the properties of the evolution between in every stages here. Okay, you can see the stage 7 until 14. What object dominant or involved in that different stages. So now the star surface temperature drops, okay? Luminosity increase slightly and the radius increase. So it will be turning into a sub-giant. If you can see from 7 to the 8th stage here. So horizontal path, okay, stage 7 to 8 is called the subgiant branch. Okay, so we have now the stable equilibrium, means the helium core is shrinking, the hydrogen fusion is speeding up, and the outward pressure increase the radius to 100 m, and also the luminosity will reach 100 m. So the stars in the ray is now opaque to the radiation from within, therefore the energy is transported to the surface via the convection. And almost a vertical path followed by the star from stage 8 to 9 is known as the red giant branch. Okay, so this star will become a red giant, and the red giant has size of Mercury orbit. Okay, and then we have this Arcturus Allomex is a type of the red giant stars, okay, in the constellation of Bootes. So radius luminosity was here. Okay, that is for red giant branch in stage 9. And then we have helium fusion in stage 10. Okay, so in stage 10, we see what happened here. Okay, so for a star with mass less than 0.25, the unbalanced state during its red giant phase will continue. However, sun-like star is simultaneously shrinking and expand, okay, when the helium begins to burn in the core. So of course, the density and temperature also change. So the reaction that transforms the helium into carbon, it occurs in two steps. So the first is to helium-4 nuclei combine to form this nuclei, and that nuclei in the first point will fuse with another helium-4 nucleus to form the carbon 12. Okay, and this is the equation of the reaction. Okay, and I think you should know this. Okay, so the high temperature of temper of 8 Kelvin is needed to overcome the electrostatic repulsion between the 4 protons in beryllium-8 here and 2 protons in helium-4. Okay. So in also in stage helium fusion in stage 10, so that helium-4 nuclei, okay, from here, okay, are traditionally known as the alpha particles. Okay, so the term dates from early days of nuclear physics. Okay, so since the 3 alpha particles are required to form carbon-12, so usually we'll have this reaction, triple alpha process. Okay, this one to plus the energy after getting the carbon-12. And for star with mass 1m, so the gas in the core now contains a vast sea of electron. Okay, and also we have this Pauli exclusion principle. Is the two or more identical fermion cannot occupy the same quantum state within the quantum system. So this is the definition of the Pauli exclusion. Okay, so in other words, the quantum mechanics prohibits the electron in the core from being squeezed too close together. Okay, so this condition known as the electron degeneracy. Okay, so continue with that electron, then we have the pressure that resists the force of gravity and supplied by degenerate electron, okay, to become unstable. So the pressure remains more or less unchanged as the nuclear reaction rate increase and temperature rise. So this condition called the helium flash. Okay, so the helium burns, okay, for hours until the energy is high enough to for thermal pressure, okay, to dominate again, and the inward gravity and outward pressure is back to equilibrium condition. Okay, so now we in stage 10. Okay, the last stage here, the horizontal branch. Okay, so this helium flash terminates the giant star and send to the red giant branch. Okay, and resulting the reduction, okay, in the energy output. So this stage 10, okay, is now stable, fusing the helium in its core and fusing hydrogen in a shell surrounding it. Okay, so this condition or a stage is known as the horizontal branch. Okay, if you can see this one, this a dark region here. Okay, so this is the also the continuation, the additional information you can read, and then we have stage 11. Okay, back to the giant branch. Okay, so yeah, evolution of this sunlight star is very complex. Okay, if you can see from the very beginning of our slide. Okay, so I think you don't have to remember all, but you just have to know and try to understand how the stage is different between each of them. Okay, so for this stage, the triple alpha process rate increase rapidly with temperature, okay, causing the helium to be rapidly consumed and making the star and send the giant branch again. Okay, so at this stage, we'll form a new coverage inner core. Okay, it will shrink in size. The energy increase. Okay, so this one is a asymptotic giant branch. Okay, in stage 11. So here, okay, so you have to uh, uh, know what is the asymptotic giant branch. Okay, so it will not run away from the luminosity, radius, and temperature. Is it increased or decreased at during that stages occur? Okay, so now is the death of a low mass star. Okay, about kematian of the bintang lah, in the low mass star. So move from stage 10 to 11. Okay, here stage 4 here, okay, until 7, and then continue here in stage 8 to stage 10. Okay, and then 10 and 11 lah after that. So at this stage, the center temperature could not reach 600 million Kelvin for the carbon fusion. Okay, so the fires go up. Okay, so what happens when the fires go up? The density will the core reach at a certain density. Okay, the electron in the core once again become degenerate and happen contraction, and also the temperature remain at 300 million Kelvin. So of course there are reaction happen there. Okay, so carbon 12 plus with the helium and will produce the oxygen, okay, and also the energy. But the collision among the nuclei are neither frequent, okay, enough to create any heavier elements. Okay, the next stage will be the planetary nebula. Okay, there is a star no longer generate energy in the carbon core. Okay, so the nuclear burning in the shell increase unstably, while the envelope expand and cool, reaching maximum radius 300. Okay, so here introducing, I think not a new term. Okay, before this they have stated about the helium shell flashes. So maybe you have to you should know the helium shell. What is the helium shell flashes? Okay, and the pulsation. Okay, I think this pulsation is quite important. Okay, maybe in, I think maybe in your midterm too, or final. I'm not I'm not remember. I can't remember. Is it include in your midterm too or the final exam? But there are about pulsation. Okay, so it's explain about the recombination. Okay, at the peak of each pulsation, what happened, and each recombination produce the additional photon. Okay, so it will increase the radiation and also resulting the instabilities. Okay. Okay, so the star now has 3 distinct parts. Okay, so it's a core, an outer shell, and also the ejected envelope. So eventually the star becomes so hot that its UV radiation ionizes the inner part, okay, producing a planetary nebula. So there are more than 1,500 planetary nebula, okay, so as we know as the galaxy. So the word planetary has nothing to do with planets, but due to the appearance of circular disks, okay, of our solar system. This one, okay, so this planetary nebula shine due to similar mechanism as emission nebula, but they originate from completely separate phases of the stellar evolution. So stellar evolution, that means including two. So we have the birth and the death of the stellar. Stellar refer to the star. Okay, so the ring shape, there is most of planetary nebula is 3D shell. Okay, so it looks brighter near the edges because there is more emitting gas, okay, along line of sight there, okay, in the edge of this 3D shell. However, this is not the case for ring nebula. Okay, it really is a ring. And spherical planetary nebula are in fact the minority, but the reason for this is not well understood. Okay, also here, okay, the picture, we can see the star's environment or the binary companions, okay, that play important role in determining the nebula shape and also its appearance. Okay, we have like a bubbles flowing into the space, yeah, or we call the Eskimo Nebula. Also have produced by a pair of binary stars, the Cat Eye Nebula, and also M29 is the twin loops of a glowing gas here. Okay. Okay, so I think you can just go through this statement here. Okay, until we go to the next one is a white dwarf. Okay, so it's a small carbon core, okay, now become the visible after 10,000 years. So this object is a white dwarf. Okay, what is a white dwarf? It shines only by stored heat. Okay, it has a white hot surface but appears dim because of its small size. So we have series B for the white dwarf example. For the white dwarf, okay, so series B is the faint binary companion of the much brighter series A. So this is the properties of the series B, okay, the radius, mass, luminosity, temperature, and density, okay, here. And we have M4 is a globular cluster. Okay, it's a distance 1,700 parsec from Earth. Okay, has 100 of white dwarf. Okay, here is zoomed in to give this nice picture here. And then we have M80 is a globular cluster, 26,000 light year from Earth. Okay, and the blue stragglers is the main sequence stars that are result of merging the binary system or the collision between the stars of lower mass. So it's called the blue stragglers here. Okay. So most white dwarfs are composed of carbon and oxygen. Okay, but it never reached the point of helium fission. Will have convective core. Okay, and after 100 billion years, all the stars' hydrogen is converted to helium and form the helium white dwarf. Okay, however, the helium white dwarf are usually produced in binary system. Okay, so this is another reaction happen in the stage 3. Okay, so this is a nice diagram. You can see for the evolution of the white dwarf. Okay, here from here we have from protostar, sunlight star, we have this red giant, Planetary Nebula, and then white dwarf, and then also we have this red dwarf evolution to get white dwarf, also from the brown to the black dwarf. Okay, so star, and it is estimated to take more than the age of the universe for a white dwarf to turn into black dwarf. So basically it's begin with the white dwarf. Okay, so comparing the theory with the reality, okay, about the M40, okay, is the fitting theoretical model of the main sequence and the giant and horizontal branches. Okay, so there are among the others known object in the Milky Way, okay, and are key indicators of conditions and the similarity between the theory and observation. Okay, stars is in each of the evolutionary stages 7 to 13 can be seen in numbers consistent with the theoretical model, and about the blue stragglers, okay, will contradict with the theory. Okay, and also we can comparing the theory with reality for NGC. Okay, I think you can read this one by your own self. Okay, about the multiple episodes and the high resolution study of many globular cluster now reveal the similar multiple sequence and chemical variations. Okay, so with the high mass and hotter stars evolve much faster than their low mass counterparts, and their main sequence lifetime are shorter. Okay, so because of the stronger gravity generate more heat, and the helium fission proceeds so quickly that high mass stars proceed in a very different evolutionary track and become the supergiant. Okay, so about the red supergiant, I think we stop here and continue for the next class. Okay, thank you.